Hello everyone, welcome back to While True Learn. We will continue with the next task, error control. Control system error. Good day, we are engaged in repair and maintenance of aircrafts. We need to be able to predict all possible problems which can happen in the air. Can you craft an algorithm that would do it for us? I love these non-specific things. The last one was give us all the data, and this one is solve all our problems. It's like, yeah, I wish I can do that, then there would be no problems in the air, right? Alright, deep news. Deep neural nets. There are neural networks that solve the so-called XOR problem, an unsolvable problem for Rosenblatt's perceptron. They have one hidden layer between the input and output layers. Such networks are called non-deep. If the network has more than one hidden layer, it is called deep. The deeper the network, the more complex dependencies it is able to recognize. For example, the current image recognition networks include several thousand hidden layers. Amazing, isn't it? Alright, stochastic gradient descent. This is the one that we bought from the eBay last time. In the game, each element in the game has a small error fix value. There's no doubles the value, use it wisely. This node doesn't work in test run. Yep. Yeah, so again, I don't know why we would use this. I know it's faster, but it increases the error rate, and we only use it during training, so it's pointless to use in test run. Anyway, in the real world, this algorithm is an upgrade of basic gradient descent, as stochastic gradient descent calculates gradient of random objects in the data set. It works fast, but may increase the amount of errors. Stochastic gradient descent is typically used with a regular gradient descent. Oh, we can stack these? Typically used with a regular gradient descent. Huh. Okay, let me actually try that, because... So gradient descent perceptron color. We pretty much know what happens here. It's going to stop at 9%, and that's the max, the best it can do. Oh, actually, you know what? I have made a mistake. So what I wanted to do was... Oh no. Forget this. Yeah, I should have... Okay. One with gradient descent. I should have tried all these in parallel. So one with stochastic gradient descent. Oh, boy. We don't have a balancer either. Never mind. Let's try one of them at a time. Yeah, it's working much faster, but wait, it still stops at 9%. Okay, I guess it's just a faster training then. Huh. And then what if I do both? So first stochastic and then the regular. What about this? Or okay, I mean, it's still 9%. Huh. Okay, I guess this is just to allow us to train it faster. Okay. Well, 9% error. This requires 97% accuracy though. So that's going to be a slight problem. I think we're going to do the same trick we did before, where if it's trash can, it requires 50 seconds of the stuff. Okay, where we're going to trash the other colors. Where if both of the layers agree, oh boy. Copy paste? Yes, okay. Okay, anyway, where if both of the layers agree that it's red, then even though we have a 9% error in each layer, because we're processing it twice, it should go down to less than 1%. There's nothing to train, let's test. looks like it's holding. Alright. Alright, the next one, Major Tom. Ping. Can you hear me, Major Tom? This is Possibility Rover reporting from Mars. My circuit's dead. There's something wrong and I can only write one email to a random address. Please help me locate Earth on the photos of Mars sky. Photos of Mars sky I've made, so I could learn to detect it and re-establish connection with my creators. They're worried sick. I won't be able to pay you with money though. There's no ATM here. Oh, and don't tell anyone I have gained consciousness. I did not. It's all an illusion. Computer sounds beep beep. Okay, well, even though it gained consciousness, it only needs me to look at photos of Mars sky and locate Earth, so it's not that big of a deal. I'm sure it's not going to be a problem. Okay, 100% accuracy, 100% accuracy. They all require 100% accuracy. Okay, so this one doesn't have any of those perceptron things. And this is all about sorting colors and shapes. Okay. 42. They both require 42, really? So this has... we have 1530. 1530. So yeah, this definitely needs some additional blue stuff. Okay, looks like we need to sort everything perfectly. 12 is exactly the number of circles we have, and then I believe the other numbers are exactly what we have. So, and we're allowed 3 nodes. Excellent. You know what? I have the perfect thing. Isolation forest. Blue circle. Else? I guess so. Ooh, okay. It's gonna be tough balancing the blue numbers. I don't know. This one takes 0.9, it takes about 1 second. It requires 42 items and we have 70 seconds. Okay, that's plenty of time. We don't need to worry about time here. And blue circle goes over here. This one goes over here. Well, actually we need to do that here. And then same thing on the other output, except now we need output over here. Now we're not gonna have the right number of blue squares and triangles is the problem. So how many do we have? We have 30 plus 10, so we need 2 more. Over here we have 30 and 20. So yeah, we can afford to lose 8. Yeah, okay. So I think all we need to do is put a decision tree. Oh, no, not quite. Oh, and we're using 4 nodes. Okay, I think I got it. So we were running into the problem where we need to kind of balance the exact number of outputs between 2 output streams, but we have 3 sources. And so we need to divide one of the sources in exactly half. And so that requires an additional node, which we're not allowed to use. So because this one is missing reds and this one's missing greens, if we merge these two, instead of using separate isolation forests for these two, if we merge these two, that's going to get us almost the same number as this. It's going to have more blues, but at least the numbers are similar. And I think this is going to have 1530 60 items, and 60 items is still enough time to be processed within 70 seconds. So this should be okay for speed. And then out of this output, we're only allowed one more node. So we're going to choose the fastest node available, which is our decision tree color. And then we're going to merge both of these outputs over here. And then we'll use the any trick to to basically divide the items evenly among the two outputs. Yep, looks like they're filling up pretty good, and we still have plenty of time left. Yay! That took me about half an hour. Ping, 32 bytes. Okay. Oh, it actually cost me money. Oh, that's right, they're not going to pay me. It's a robot on Mars. That's okay. Yeah, I'm happy to help a robot on Mars. Okay, next one, a package for you. Hi there, we are Sort Stuff, the postal company. Every day, thousands of parcels pass through us. No one likes it when their package from Ola Express gets sent somewhere else by mistake. We've been using sorting system for incoming mail for a long time already. It distributes packages depending on the marking of the order, but it makes too many errors. We would like to reduce the number of such instances to the minimum. Okay, throw away or keep everything that's either circle or red. Throw away the rest. And it requires 94% accuracy. We're allowed 2 nodes. So I'm thinking the perceptron isn't even going to... okay, it's barely going to work. Okay, let's try that. Perceptron color, we can accept all the reds immediately. Perceptron shape, yeah, sorry. Need to train these first. Okay, so I guess I'll train them separately. Gradient descent or stochastic because it's faster. Train this. Shouldn't it just... oh, because, yeah, okay. I thought it was going to notify me when it reaches 9%, but it's because I had another one here and that one hasn't been trained yet, so. Okay, now that's done. I don't want that. Okay, let's do a perceptron color. I'm putting this first because it's faster. So it's going to do a first pass on the items, filter out all the reds, and then the green and blue, which is going to be a smaller number, is going to come over here, and then I'll keep all the... I can't trash anything? Excuse me? Okay, I'll just feed them back then. That's the odd way of trashing stuff again. Circles, go in here, square, red, go in here. I guess so. If that doesn't work, I don't know what to do. Okay, yeah. Accept. Alright, next one, fix our engine. Fix our search engine or whatever. Or whatever. We greet you on behalf of Google Dynamics. We tried to use neural networks to optimize our search engine, but it turns out that they require way too much server power. So we want to outsource this work to you. Try to use decision trees or linear regression or whatever. It's accurate enough, we don't care. In the meantime, we'll focus our efforts on what really matters, programming AI systems for killer robots. Okay. Let's see what's happening here. Okay, I'm guessing the number of items. Ooh, we're going to have to think about distributing the numbers. We have a total of, okay, that's 6 times 18 times 1, 2, 3, 4, or, God, mental math. Okay, 6 times 6, that's 36. Okay, 72 items, 50, 60. Okay, not too bad. So if we put all the reds here, we're going to have 18, and then we need, or I guess 6, 6, 6, 6, 6. That's going to give us how much? 30. Okay, yeah. I think we're going to have to use almost the full number of each input stream, and we're allowed 2 nodes. 2 nodes. Yeah, seriously. Okay. Alright, I'm seeing, okay, if we take all the squares, we have 6 times 5, which is 30. That's going to be enough for this. If we take all the greens, okay, bear with me, all the greens, we're going to have 30 as well, but the squares are going to be shared, which is kind of okay because we have a margin of 5. Wait, no, that's not okay. Yes, we can't do that. We have to have some... Oy. Okay, yeah, so I was thinking about how to divide the input stream and sort them into the output streams, right? So we can either divide by shape or color. It's pretty much the only options we have. So the most efficient way we can divide is by dividing them into as many categories as possible with the same numbers in each category. So over here, we're going to use the random forest to do the division. Over here, if we divide by color, so red, blue, and green, we're going to get the same number on each lane. So that seems like the most efficient way to divide. And then we actually have output streams that accepts each one. So red can go in here, blue can go in here, and green can go in here. This one doesn't accept blue circles, but it doesn't matter, we don't have any blue circles anyway. So this is an even division of all the output streams. And then over here we're going to do something similar. We're going to use the random forest again, except we're going to divide by shape. So all the circles can go here. Again, no blue circles are available. All the squares can go here, and all the triangles can go here. And each output stream is getting one output from each of the random forests. So that we're missing items. Alright, since we were missing items over here, that means we had too many items over here. And I'm seeing, since we're already getting all the blues here, and we have 12 blues available, that's already enough to fulfill this output stream. So there's really no point in sending the circles over here. So the circles we can actually send over there, which means we only need to divide this among 2 output streams. So instead of doing that, we can just divide by color, red and green, and then all the reds come over here, all the greens come over here. This way, this input stream is going to be divided evenly among these 2, and then input stream number 3 is going to be divided evenly among these 3, with output stream number 4 receiving just the right number of items. And then output stream 0 and 2 should be correct as well because they're getting the same number of items. Yep. Great. Okay. Looks like we have 2 missions left and then we will get to another story segment, so let's finish those. Recommendation system. Hello, we need to build a smart system that can help students learn English faster. This system needs to be able to assign an appropriate curriculum to each student. Can you design something like it, please? Okay, we got another deep news. Neural networks architecture, ReLU. In neural networks, programmers use a vast range of different neurons. Inside each neuron, a math function is located. For example, Rosenblatt's neuron used a linear function. Simple neural net, which can solve XOR problem, uses the ReLU function, which is apparently 0 when it's negative and a linear function when it's positive. These functions are called activators. For different tasks, people use different types of activators. To solve more complex issues, a combination of neurons with different activators is used. Yeah, this ReLU thing was mentioned in the info card for the perceptron. I'll just show you real quick. Right here, ReLU. That's one of the functions, and the other functions, tanh is the hyperbolic tangent function, and sigmoid is a kind of low and high function, I think. Anyway, we're allowed 5 nodes. We're picking out specific color shape combinations. Accuracy rating isn't that specific, but we can't just keep one shape or the same color or anything. It still has pretty okay requirements. Okay, so 5 nodes. Okay, so I think I know what to do now. This is not too bad. Stochastic. Let's train this one first. Gonna leave that to the side, and then we're gonna use perceptron shape. I'm gonna train this. Alright, now we don't need this anymore. We're gonna use perceptron color first because it's faster, and it's going to divide all the colors evenly, and then we'll have 3 perceptron shapes in parallel for each of the colors. And then we have a trash can, which we can finally use. Yeah, this is the red circle, goes over here, red everything else gets trashed. This is green, green square goes over here, everything else gets trashed. Blue triangle goes over here, everything else gets trashed. Yeah, and that's exactly the 5 nodes. Okay, it's very straightforward. And the last one is going to be meteorite alarm. We've detected some dangerous asteroids in space. Now we need to be able to predict their trajectories in order to avoid potential catastrophe. We need an algorithm to calculate that, and fast. Some of those space rocks may destroy the moon. Oh, just the moon, okay. At least it's not Earth. Alright, we're allowed 8 nodes, that's pretty okay. 95% accuracy, and we only have the perceptron, so we're gonna have to do some fancy accuracy jiggling there. Only greens and no triangles. And we need 100 of these, so we pretty much need all of them. Okay. We have 33 seconds too, so... Okay, we're gonna do perceptron color for sure. Let's do a perceptron shape because we can actually train them in parallel now. So the first step is just to train and get the nodes that we need. Yeah, I know you can probably do it faster with the predefined thing, but anyway, I've been doing this all along, so why stop at the last mission? Okay, we're gonna do color first. So we only need, we're allowed 8 nodes, so we can totally do these in parallel. We don't need a color here because there's only one color. Trash can, We're gonna throw away all the reds and blues. Yeah, actually 8 nodes, okay. We have to have 95% accuracy. So why don't we do another layer of perceptron color? So all the ones that we think are green, we're going to process them again. And then, yeah. The reds and blues still get, the misclassified ones still get trashed. And the green ones we're going to use for something else. Oh, this one doesn't even require more filtering, so why don't we I'm pretty sure I'm going to have to make this more efficient, but let's just try this for now. All the green can go immediately over here. This one requires more filtering. So we're going to use the perceptron shape. All the green ones come over here, and we're going to take the circle and squares, throw away the triangles, and over here we're going to do the same thing. Circles and squares, except now we can actually we can do one more node. So I'm going to do the double layer thing again, where we take, let's see, all the triangles, so we throw away the triangles, and then the other shapes come in here. Oh, that might not be fast enough. Actually, yeah, that should be okay. And all the triangles that got misclassified come over here, all the other shapes come over here. Let's see. I only have concerns that it might not be fast enough, but we will see, I guess. Yeah, looks like the accuracy is okay. Numbers, no, we ran out of time, so it's not fast enough. Okay, so during the test run I noticed that input stream 3 wasn't finished processing, or it was processing very, very slowly. And that's a main reason why we ran out of time. The other inputs had finished processing pretty quickly, and it was only input stream 3 that was getting delayed. So I'm thinking we're gonna need to do a load balancer here to process them in parallel. And then instead of doing 2 stages, we're just gonna keep 1 stage. The accuracy is not going to be super great, but I'm hoping with the help of all the other input streams that have higher accuracy, we can still achieve the 95% rating. So we're just going to do 1 layer of perceptron over here, and then we're still using 1 more node than needed. So over here, this one I want to keep the 2 layers because red and blue are the majority of the mistakes we're going to make. So if we keep only 1 layer, we're going to have way too many mistakes coming in and ruining our accuracy. So I want to keep 2 layers here. But here, because red and green are a minor number compared to the number of greens we have, even if we allow some mistakes to come through, it's going to be a small percentage. It's not going to be 9%, it's going to be less than 9%. So I'm thinking we can also just delete this one and hook it up directly to a perceptron shape, and hopefully that accuracy is going to be okay. Cool. Alright, looks like we have finished this section of the game, and we are very close to the end of the game. Looks like we are at our last epoch, Deep Machine Learning 2012 to nowadays. This is going to be the last epoch, and we are 97% done with the game. So next time we come back, we might just be able to finish the game. That's it for the gameplay portion of this episode. Stick around if you want to hear more about neural networks, otherwise you can skip to the next episode now. In this episode, we read a lot more details about neural networks, like activator functions and hidden layers. These details of neural networks architecture are heavily inspired by how biological neurons work in animals. very roughly speaking, nerve cells are also connected in networks, where each nerve cell can receive inputs from many other cells and can also send outputs to many other cells. Signals are sent between cells using quick electrical pulses called action potentials. The frequency of pulses a cell sends to its outputs will depend on the frequency of pulses it's receiving from its inputs. Some inputs can activate a neuron, where higher input causes the neuron to fire pulses faster. Some inputs can inhibit a neuron, where higher input causes the neuron to fire pulses slower. But in any case, usually there is a minimum threshold. Below that threshold, the input will have almost no effect. That is what the activation functions used in artificial neural networks are trying to replicate. We were given many examples of activation functions like ReLU, the hyperbolic tangent function, and sigmoid function, but in all cases, they have a low zone where the input leads to very low output, a transition threshold where the input quickly starts taking effect, and a high zone where the input leads to a high output. Taking linear combinations of these functions can get you more interesting functions, and you can even extend this to multiple dimensions, but they cannot be used to build a function like this one. This is essentially the output of the exclusive OR function or XOR function, and this is the so-called XOR problem that the game made references to. In order to solve the XOR problem, or in other words, make a neural network that can produce the XOR function, we need to use deep neural networks consisting of many layers. Multiple layers of nerve cells is common in biology too. For example, the human vision system starts with cones and rods, which are simple light detectors, but then they are connected to various layers of cells in the retina, which are responsible for recognizing simple things, like contrast, edges, and orientation. That information is then fed into deeper layers for detecting more advanced things, like shapes and movement, and then countless more layers further into the brain. Currently, we don't even have a good understanding of how human vision works, so it's no surprise that computer vision is still a very challenging problem. That'll be it for this episode. I hope you enjoyed. Thanks for watching and see you next time.